Welcome. In the last lecture, we have studied semilinear equation, semilinear evolution problem. And there we have stated one theorem saying that if the additive function is continuous in time and uniformly Lipschitz in the second variable or space variable, okay, then and also the operator A is infinitesimal generator of C0 semigroup. Then for any initial point from the Banach space, one can get one mild solution. Okay, it has a unique mild solution, and moreover that the dependence on the mild solution on the initial data, that dependence is Lipschitz. So it has Lipschitz dependence. Okay, so this theorem we have seen in details, we have seen the proof in details. Now, when this is done, we ask the next level question that what about the classical solution? Okay, for all other earlier problems like initial value problem, homogeneous initial value problem, inhomogeneous initial value problem, or even evolution problem, homogeneous and inhomogeneous evolution problems. So for those, we did not need to ask the question that whether the mild solution exists, because we used to write down, we actually have written down the mild solution formula provided the operator A has sufficient stability. I mean, in the sense that that generates either a semigroup, C0 semigroup, or it generates a evolution system. Okay, so only immediately after obtaining an evolution system or semigroup, we could write down the mild solution for those problems. But here, when we are discussing semilinear evolution problem, then even after obtaining the semigroup generated by the operator A, since the additive data is nonlinear, one needs more property on the additive data, how it depends on the space variable. So and then if that is Lipschitz, then only we can ensure existence of a mild solution. Here the mild solution does not have any expression, rather we write down mild solution of the equation of the original problem as solution of an integral equation. Okay, so the question arises that when the integral equation has a solution. So that was the reason of discussing this. Okay, but however, the question what we generally ask for every Cauchy problem, whether it has a classical solution, or in other words, what are the sufficient conditions on the operator, initial data, and additive terms so that one can assert that the problem has a classical solution. So here, for this problem, this regularity theorem asserts that, so let A be the infinitesimal generator of a C0 semigroup on X, and additive term F is continuously differentiable. So this F is a function of two variables, time variable and space variable. So here, so we have assumed F is continuously differentiable. So it is in line of the assumptions what we have made for IIVP. So there we have stated couple of sufficient conditions for existence of classical solution. There also we have taken the additive term to be C1. Okay, in one of those theorems, and also we must take the initial data coming from the domain of definition of A. So X belongs to dA. Okay, so we have taken these assumptions in the line of earlier theorems for some special cases. So here one must be careful that this is C1 in with respect to this is a function of two variables, correct? Not only time to X, but time and space together. Okay, so differentiability in that sense. Okay, so the mild solution is a classical solution. Okay, second assertion is that, first assertion is that, okay, so it has a classical solution, and then the classical solution, whatever we write, coincides with the mild solution. Okay, fine. Or in other words, basically one can say that the mild solution becomes the classical solution. Or in other words, the mild solution gains sufficient regularity that it belongs to the domain of definition of the operators involved, which appear in the equation. Okay, so that is all about the regularity theorem. We have stated similar theorems for earlier problems. So for this, semilinear problem, this is the statement. There are some other alternative, theorems with some other type of sufficient conditions, and then after stating those, we would prove this, regularity theorem. This point 18, this statement we are going to prove in details. Okay, so let us see some other, type of statements. If A is the inferential generator of a C0 semigroup GT on a reflexive Banach space, capital A, so here we are assuming a lot to the space X, okay, so then we may need to assume less on the additive term F. So here we are not requiring that to be differentiable, but only Lipschitz. So Lipschitz function on the on these two variables, time and space variables. Okay. So then for each x in dA, so the domain of operator, the mild solution is a classical solution to the semilinear evolution problem, SEP. Okay, so let us recall what is the SEP, the full expression which appears earlier. So this is the SEP. D phi dt is equal to a phi t plus f of t phi t. So here the dependence of f on phi need not be linear. So that is the reason we call this semilinear evolution problem. Okay. Next, before going to the proof of this regularity theorem, we make some comments. The conditions in above two results do not ensure uniqueness. Do not ensure uniqueness of classical solution to SEP. However, some further stronger condition is required, so that ensures uniqueness. So this is one of the sufficient conditions. So let F is a map from, so this is an additive term from time and space, but here in space, instead of x, we put capital Y. So assume that if you restrict F to the time domain, and then instead of whole Banach space, just restrict to the subspace Y, where Y is a domain of definition of the operator. So then the range, if the range is also in Y, okay, and then this map is uniformly Lipschitz in Y. So here this is uniform Lipschitz in Y. When we say that, that means that to get the Lipschitz property, we would consider the norm which is endowed, which is given in Y. Okay, so Y is endowed with the graph norm, correct? So with that, we need to have this F to be uniformly Lipschitz in Y. Okay, uniformly Lipschitz, that means that the Lipschitz constant that does not depend on time. Okay, one can get a Lipschitz constant which does not depend on time. And pointwise continuous in time variable t. So with this time variable, it is continuous. With this second variable is Lipschitz, but here we are putting much smaller subset and some other different norm. So in under this condition, if x is in the domain of A, okay, and A of course generates scissors and all those things are as before, okay, so then this semilinear evolution problem has a unique classical solution in the interval smallest to capital T in the total duration. Okay, so next we go to the proof of the regularity theorem. So we are going to prove this theorem. Okay, so here the main idea of the proof is that since f is given this way, okay, So we would use the earlier theorem which ensures existence of a mild solution. So given these conditions, we would first ensure that it has a mild solution, and then we are going to show that the mild solutions has sufficient regularity. Okay, so that is the main idea. So it has many steps. We would go step by step. So as f is in C1, okay, f is continuous, correct? So here we are assuming it is continuous differentiable, so it is indeed continuous. And since it is C1 here, okay, so that means it is differentiable, and the derivative, if we consider the derivative, okay, so the derivative, okay, so that is on the time domain, okay, and then we are going to get the Lipschitz continuous in space uniformly on S to capital T. Since it's differentiable, so derivative we are going to get, but the derivative may depend on time, but the time varies on a compact set. So, and because of continuous derivative, we would get the derivative would be bounded there. So you would get the derivative, okay, so that function, I mean that the Lipschitz constant, whatever I'm going to get, would be upper bounded by a fixed constant. So you get Lipschitz uniformly on the interval S to capital T. So then we can apply the theorem which asserts that the SCP has a unique mild solution. So SCP has a unique mild solution, and we call that mild solution as phi. Okay, so it is actually var phi. So phi, which is itself a continuous function of time. So it is actually path, a continuous path, okay, on the Banach space capital X. Okay, so next we need to show that the phi is continuously differentiable. Okay, that means, in the equation, phi appears on both sides. Left hand side d phi dt appears, so that should be meaningful classically, correct? So d phi dt should exist. So phi, we are going to show that it's continuously differentiable. So we recall the definition of phi. So phi of t is this is the integral equation which the mild solution must satisfy. So phi of t is equal to capital T of t minus s x. X is the initial point. Capital T is the semigroup generated by the operator A. So phi t is equal to t of t minus s x plus integration small s to t capital T of t minus r f of r comma phi r dr. Okay, and then we consider the Fisher derivative. Okay, so this Fisher derivative is the derivative of f with the second variable. So bs comma v is defined as del L v of f is v. Okay, so this thing belongs to blx. Okay, so that is the meaning of derivative here, because the derivative of these functions with respect to the Banach space valued function depend on the Banach space. So here the derivative with respect to v would be a bound linear map from the space to space itself. So that is the derivative, and we can write down this because it is already given that f is in C1. So that means this derivative exists. So we can do that. We also define g, another function g of t, which is defined as capital T of t minus s f of s phi s plus a composition capital T of t minus s, this is semigroup, this is generator, x plus integration small s to t capital T of t minus r del L t f r phi r dr. So what does it mean? That means del L t f of something is basically the partial derivative of f with respect to the first variable. Okay, whenever I want to take the derivative with the second variable, we write down del Lv. When we would like to write down the derivative of f with respect to the first variable, we write down the del Lt. So this is the form of gt. It is not now yet clear why do I need to consider such complicated long expression function. Yes, so actually this appears. This appears in the proof. Intuitively, I can say that, okay, when we are going to take derivative, some terms would arise. You understand that if you take derivative of this, the a terms appears. So these terms basically appears, as terms which arises after taking the derivative. You see the derivative also appears here. Okay, this is gt. So we at least know from the expression that g is continuous path. Okay, so is a continuous function of time t. Why is it so? Because this as a function of t, this is tt of something, okay, some constant. So t is Caesar semigroup, so this is continuous in t. Here, for the same reason, that since x is coming from the domain of definition of a, so this is in the domain of definition A, so this makes sense. And since tt is Caesar semigroup, so this is continuous. So att minus sx is same as t minus ax. So from that we are going to get this is continuous in t. So here what we need just the integrability of inside term to get the continuity of t, and that is true because here since f is in C1 and then on the closed interval it is continuous also. So the derivative is also continuous on closed interval. So this is bounded during that interval. So this would be locally integrable, or basically is integrable also. So we are going to get this thing. Okay, so that asserts that g would be continuous. Okay, so now what we have this b notation. Okay, so that we have into this is nothing but a member of the member in the BLX, and then a GT. And now we are studying the property here. So R goes to B R phi R. So phi is this. Okay, phi of R is a point in the Banach space. So as a function of R, and the first variable is R here. So now we are studying this map R to B R phi R. So this map is also continuous map. Okay, why is it so? Because of this C1 function. So this derivative is continuous. So due to that, and since phi is also continuous, so it's composition of these two maps. So this is continuous. Okay, so R2 B R phi R. So this map is continuous. Okay, so this is continuous, and then we consider this map t comma v to b t phi t v. Because b is v. Okay, this whole thing is a member in the BLX. So this, if you apply to a member in the Banach space X, then you get a point in the Banach space X. Okay, so here if you apply that to V, you get some point there. So now if you choose an arbitrary small t in this interval and an arbitrary small v in the Banach space, and then you consider b t phi t v. Okay, so this as a function of time t and v. Okay, so this is also continuous in t and uniformly Lipschitz in v. Uniformly Lipschitz in v is trivial because this is actually linear in v, correct? And then this changes with time, but this changes continuously. So as stated here, and on the compact set we are considering here. So the norm of this linear operator can be upper bounded by a fixed constant. So that would give me uniformly bounded. So this is family of linear operators which is uniformly bounded. So that would give me that uniform Lipschitz property also. So this is uniform Lipschitz in V. Now next, so what we do is that we introduce another function. So here at this stage, I understand that I'm not giving much motivation. Why am I using this, introducing these new operators and functions, so b, g, and now we are introducing w also. But that will be clear when we go to the details of the proof. So let wt be the solution to the following, integral equation. Wt is equal to gt, g as earlier defined. So g is defined here. So it has 1, 2, 3 additive terms, and then we have Wt is equal to Gt plus integration smallest t capital T of t minus r br phi r w r dr. So w appears both sides, so this unknown appears both sides. So this is basically an equation. So consider this equation is another integral equation, okay, and assume that w be the solution to the following integral equation. Okay, so then the proof of existence of uniqueness of w. Okay, so basically existence and uniqueness of the solution of this equation is very much same as the existence and uniqueness theorem of the mild solution. Okay, so there we had a different term here, tt minus sx, something like that, and here we did not have b but some f terms were there. But what I can write down this whole thing as, we can treat this as this part as f, okay, and can check that whether the conditions in the theorem is satisfied by the condition here. If that is so, okay, so then we can assert that existence and uniqueness. Okay, so this is true because the conditions which just we have expressed here, that the Lipschitz continuity in the v variable. Okay, so as a function here, so for mild solution, this is the form, and then in the equation, new equation w, there instead of this we get gt, and instead of f we get these b, these things, correct? So here br phi r w. Okay, so here it is not semilinear operator, it is precisely linear operator. Okay, so here using proof of earlier theorem, the sufficient conditions for the applicability of the theorem is true for this case also. So we can apply that to obtain that this has a unique continuous solution. Okay, so Wt exists. So why am I talking all this? Because just to ensure that Wt exists, okay, such there is a continuous function Wt, okay, which satisfies this. And now we consider f of r comma phi r plus h minus f r comma phi r. Okay, so this increment. So this increment, if we would like to apply the differentiability property of f here, we would be able to get that this difference of this second variable increment is equal to b of r comma phi r, the derivative, okay, at the point phi r, so this left-hand point here, and then multiplication with this difference phi r plus h minus phi r plus some other error term w1 rh. As h tends to 0, this 1 over h w1 must go to 0, correct? That is implied by the differentiability of f, this is the second variable. Okay, so this is the notation. Basically I would like to introduce the w1 here, so the error term here. Okay, so next we consider the increment to the first variable here, the difference here. Second variable looks as it is. So first variable is f of r plus h phi r plus h minus f of r comma phi r plus h is equal to del L t. So now since it is increment with respect to the first variable, and f is differentiable, continuous differentiable, so I would be able to write down this difference using the derivative with respect to the first variable. So we write down del L t of f of r comma phi r plus h, okay, times h is the increment here, this is r plus h is the increment, plus another error term w2rh. So only one thing we know about this error term is that 1 over h of w, this goes to 0, correct? So 1 over h norm of wih, okay, so that goes to 0 as h goes to 0, okay, uniformly on this. Okay, so next what we do is that we aim to show that phi is differentiable. Okay, so that is our main goal, that phi is differentiable, and the derivative is w. Okay, so now it is clear that why am I introducing these notations like g, b, w, etc. See, I mean, phi, I'd like to show that it's differentiable, that then the derivative is also very relevant and important thing. And there, that the derivative of phi, okay, we are going to show that is w. And to write down w, I need to write down this integral equation, and this integral equation involves g and the operator b. Okay, so that was the main reason to introduce this function g and b, just to get the w. Okay, now consider this wht. This is also another error term. So 1 over h phi of t plus h minus phi of t minus wt. Okay, so we need to show that this error term goes to 0. Okay, if I can show that this error term goes to 0 as h tends to 0, then we would be able to justify that phi is differentiable and the derivative is w. Right? We would be able to assert both the things. Okay, if we just prove that wh is equal to goes to 0. Okay, in the subsequent slides.